The next invited speech will be presented by Professor Massimo Vaccaro, and the speech will be concerned SP orbits of Isoclinic subspace in the real Grassmannians. So, welcome, Professor Massimo.
First, I would like to greet Maria, first of all. Is everybody watching me?
Yes.
Okay. Let me first greet Maria. If she's still there, I don't know, but I'm very happy that before I saw her, I've seen her after a long while. I think more than 2 years. I think so. And then I want to say that for me, it's a big pleasure to be here, taking part to this conference, where we all remember our dear Professor Lawrynowicz. For me, he was surely a teacher from his wide knowledge of many different fields of mathematics. But he also was a special person. I have, and I keep it in my heart, for his kindness, for his availability, for his sweetness, I would say, ever since we first met in Rome. I hope this conference will continue in the future, also because I'm sure that when we will meet again, hopefully in Bedlewo, our thoughts will always go to him, who made this event exist, possible. So, ciao Maria, and let me start. I have to share my video. Okay, I hope I'm sharing. No, that's better. Go on.
Yeah, it's okay. We can see. We can see.
Okay, good. I just would like to take this away. Can I do that? Yeah. Here. Okay. Okay. So my talk will be on the orbits.
Excuse me, can you make full view? There is a view, full screen mode. It is better for visibility.
Do I have full screen mode? Do I don't know. I hope so, but I'm
Control,
not.
Control L.
Control L?
Probably, yes.
Yes, okay. Do you see better now?
Yes. Yes, thank you.
Okay, so my talk will be about these orbits in the Grassmannians, the orbits of isoclinic subspaces. You can ask why such a strange topic about isoclinic subspace. Actually, the orbit of the normal subspaces, not isoclinic, is not yet determined. So this little part about isoclinic can be strange, but actually the reason is exactly because this is my fourth paper about these orbits in the Grassmannians, and in the second one, you see here in the SPN orbits in the real Grassmannian, which takes all the subspaces, any k-dimensional, I developed a theory. I reached, which is stated in a theorem, and I also built up a procedure to find out if two subspaces, the invariance, to find out the invariance, so to detect if two subspaces are or not in the same orbits. And but this procedure, which most of the time can be applied, in some cases cannot be applied to Kerr. You need some further investigations, and so among these cases that they cannot be solved by the procedure that I set up, are the isoclinic subspaces, which are some of the degenerate cases that I deal with. Not all the degenerate cases, unfortunately, but are maybe the most difficult cases that is not solved. I still have other cases to solve, but these are very complicated. And finally, about these isoclinic subspaces, I could manage to find out the invariance determining the orbits. Of course, the story is not finished, but it's a big step forward for me. So here, let's just go to the point. Let's first show the environment where I live. I said I I study the orbits in the real Grassmannian of 4n dimensional vector space. 4n because the representation of SPN is on a 4n vector, real vector space. So we consider a 4n vector space. And inside this 4n vector spaces, I consider all the k-dimensional subspaces. SPN is the group of, it's called the quaternionic unitary group. It's the group which preserves the group of automorphism of an Hermitian hypercomplex structure. So we endow our vector space real, I said, of dimension 4n, of an hypercomplex structure, actually of the span of a real of an hypercomplex structure, which is called a quaternionic structure. So we have a vector space of dimension 4n and a quaternionic structure inside. Okay. The typical, let's say, a prototype of an hypercomplex and also quaternionic Hermitian vector space is the Hn, the n-dimensional quaternionic numerical space, which has you can see easily. I don't go into details because otherwise we never finish. But as the structure of an Hermitian quaternionic vector space, and we can take from this model the Hermitian product defined here on the formula number 2 in the last line. That it's a connection between the Hermitian product, which is canonical in Hn, and the real part of the Hermitian product. So you see, if you take two vectors x and y and you make the Hermitian product, it's a quaternion. Of course, you get a quaternion whose coefficient of I, j, and k are given by the real part of the Hermitian product of these two vectors, of this x, xiy, xjy, xky, where I, j, k are exactly the multiplication by minus I, minus j, minus k, and determine an hypercomplex structure. So anyway, this is just the model. Let's go on. When studying the orbits in the Grassmannian, the principal angles, you see here, the principal angles, maybe many of you knows, I would like to have the arrow, not the hand. I don't know if, it play an important role. I don't know if everybody knows what principal angles are. I will define a bit later, but just to show that they were introduced in 1875 for subspaces of Rn by Jordan. And Jordan showed that if you have not a subspace, but a pair of subspaces and another pair of subspaces, the first pair map into the second pair by the orthogonal group, if and only if the principal angles of the first pair are equal to the principal angles of the second pair. So in determining the orbit of a pair of subspaces, principal angles are very important. So why now I talk of pairs? Because now I have to determine the orbit of one subspace. But it was showed, it was showed by Tasaki, I think, that if I take a subspace in a real vector space, and I act with a group not SON, which determine only one orbit, but with a smaller group, which is the unitary group UN, then I have that the principal angles between the pair U and IU, I is a complex structure, and W and IW, if they are the same, the principal angle between these pairs, then U and W are in the same UN orbit. Okay, so the principal angles were introduced and were very important. They already start to show their importance in the orbit of in the Grassmannian under the UN group. But UN is a bigger group, and we are talking about SPN, which is a smaller group, so we have more orbits. Before going on, I said here, we recall the definition of principal angles, scalar angle, isoclinic subspaces, and standard subspaces of Q-symmetric form. I need to give these definitions because then I use the thing. So we go on with the speech, but later I need some definitions. The principal angles, which are very important, between a pair of subspaces of a real vector space are defined in this way. you see this formula, but maybe the formula can be confusing, but it's written under more simply what's the meaning. In words, the procedure is to find the unit vector A1 belonging to big A, which is a vector space, and a unit vector B1 belonging to big B, is another vector space, which minimize the angle between them, and call this angle θ1. So we look in the two vector spaces for the two vectors, one in one space, one in the other, that they realize the minimum angles, and this is θ1. Then we consider the orthogonal projector, orthogonal complement in a big A to A1, and the orthogonal complement in B to B1, and again we look for the smallest angle again, and so on. We iterate, and then we get up to K, which is the dimension of the smaller subspace, K principal angles. We get the K principal angles. Okay, we take first the smallest angle, then we go on the complementary, the smallest again, then the smallest, and we have a set of K angles, which are the principal angles between the spaces. Okay, this I see. The principal angles are the diagonal entries of the orthogonal projector stated in the theorem of Afriat. Okay, for people who are interested, if you have a pair of subspaces AK and BL, and you make and you write the Gram matrix, that is the matrices of the scalar product between an orthonormal basis of one space and the orthonormal basis of another, it's always possible to find an orthonormal basis in one and an orthonormal basis in B, which diagonalize these Gram matrices. And with the entries in the diagonal, they're all bigger or equal to non-negative. This is very important because it's written there after the principal angles between a pair of subspaces A and B can be defined as a singular value of the orthogonal projector. I mean, singular value, when you know singular value decomposition, is something which in algebra is very used. So you can find the principal angle by the singular value decomposition, a well-known technique. The Keller angle instead is defined for real vector space with a complex structure. Okay, you need to have a vector, so dimension of the vector space should be even, 2, 4, 6, and we have a complex structure, I. In that case, we speak of Keller angle between two vectors is given by the scalar product between x and iy, divided by the measure of the vector x wedge y, and is an angle which is generally between 0 and y, and it's straightforward to check that that the Keller angle is an intrinsic property of the oriented two-plane linear span of x and y. So any two vectors you take in x and y, and you make this scalar product, and then you divide by the measure of the vector, you get always the same number. So it's invariant, doesn't depend on x and y, of the two-plane. So we speak of the Keller angle of a two-plane instead of two vectors. In our case, of course, in our quaternionic structure, we have many complex structures. We don't have only I. We have the whole Q, SQ, the sphere of complex structure. So we speak not of Keller angle, but we have to put in front of the Keller, which is the complex structure we're talking about. A Keller angle, I, J, K, depends on which structure, complex structure we are considering. So in this formula, you have to put X, I, Y, B, Y, depends on the structure. Then we recall something also of linear algebra, that if you have a skew-symmetric form, the skew-symmetric form admit a standard form with respects an orthonormal basis. This orthonormal basis, from now on, we will call a standard basis. And the linear span of the two planes, in this way, I is odd, and this is like x1, x2, or x3, x4, x5, x6, is a standard two-plane. And all the subspaces associated to the same value of not zero of this scalar product are called standard subspaces. They can have any dimension. The two planes instead have, of course, two dimensions. Now, the last is the definition of what's an isoclinic subspace. We say that two subspaces A and B are said to be isoclinic if all the principal angles between A and B are the same. So we have many principal angles. If they're all the same, we say that these subspaces are isoclinic. They have the same angle, the same principal angle, one principal angle, which is called the angle of isoclinity. Okay, we have K principal angles, all the same. So we speak about angle of isoclinicity. From now on, we denote, because we talk about this set, by IC2M, the set of 2M dimensional subspaces of D, such that for any A, this is the sphere of complex structure, SQ, Q is the quaternionic structure, SQ are the linear span of IJK, which is an hypercomplex basis, admissible basis, with A squared plus B squared plus C squared equal 1. So the sphere. Then for any A in the sphere of complex structure, for any complex structure admissible, the pair AU is isoclinic. So in our vector space, we say that a subspace is isoclinic if, with respect to any complex structure, we have U, and then we have AU, BU, CU, DU, all the complex structure. Then the angles between A and all these other subspaces are all the same. Not all the same between them, but all the same. That A and EU are isoclinic. A and BU, sorry, U and AU are isoclinic. U and BU are isoclinic, and so on. Why we consider only even dimensional vector spaces, subspaces, the set of 2M? Because the odd dimension are only what we called real Hermitian product subspaces. That is, subspaces such that U and AU are always strictly orthogonal. And these subspaces, it's easy to prove, all real Hermitian product subspaces share the same orbit. Okay, so if you take 2M plus 1 subspaces, isoclinic, then they are all in the same orbit, and they are called real Hermitian product subspaces. So for even the odd dimension, no problem. We know that there is only one orbit for everyone. So we consider only odd even dimension. Before I said even, I should say odd. Okay. And so I said, after Tasaki said that to determine the orbit of a subspace under UN, it's important to consider the principal vectors. It's normal, it's natural to try to check if in this case we can still consider the principal vector only. I mean, if I have U, I consider IU, JU, and KU, where I, J, K are an hypercomplex basis, and I check the principal angle between U and IU, then U and JU, U and KU. And I say, can I say that if another subspace W has principal angles with IW, JW, and KW the same, they are in the same orbit? Answer, no. In this case, it's not possible. This condition is only necessary condition. We need something more, unfortunately, because the detection of principal angle would be very easy. But in this case, it's not enough. We need something more. What do we need more? It's written in this theorem here. This theorem is the, let's say, the general theorem for defining the invariance of two subspaces, the invariance of subspaces belonging to the same orbit. So we say, okay, we choose an admissible basis, I, J, K. I don't know if I said at the beginning, maybe I forgot. I, J, K are three complex structure, an hypercomplex structure, which means that I, J equal minus J, A equal K. So if I have a vector space, I take three endomorphism which squares to minus identity because are complex structure. These are three complex structure. A square equal minus identity, J square equal minus identity, K square equal minus identity. Three endomorphism, any. But you have to have that they are skew metric that say ij equal minus ji, ik equal minus k, and iji multiply j equal k, this is what we call an hypercomplex structure. Okay, the span of this structure is a quaternionic structure. In a quaternionic structure, we have many, let's say, bases ijk, many. One of these is called an admissible basis. Okay, so in this work, in this article, I fix at the beginning an hypercomplex basis, let's say a basis of Q, and I consider this base fixed. So I choose a fixed admissible hypercomplex, if you want, basis. And then we say that necessary and sufficient condition for a pair of subspaces U to belong to the same SPN orbits as stated in the theorem. So let ijk be an admissible basis of the quaternionic structure. The subspaces UM of same dimension, of course, and WVM of V are in the same SPN orbit if and only if they share the same ijk principal angles. This is what we said before. This is a necessary condition, so we have to add this one. Let's say the theta I du equals theta I dw, theta j du equals theta j dw, theta k du. This, this is sufficient in complex under the action of UN, of course, we said, and only one of this. We don't have three, we have only one. But in this case, no. And then we have to, the difficult part is this, there exist three standard bases, which are the bases of the skew symmetric form, I said, omega I, omega j, omega k, in standard basis in U and three standard bases in W, with respect the Gram matrices that I call Cij. Cij is the Gram matrix of xi, x and y, and Cik is the matrix of x and z. In both subspaces are the same. So these bases here in the first subspace, they must have the same relative position one with the other. That is the Gram matrix, which is the matrix of the projector, more or less, should be, it's an orthogonal matrix, it should be the same. But we have to find three bases because we can find millions of bases in one, millions of bases in the other. So how do we find if they exist, such bases? And this is the big problem. Okay, I have to find three standard bases, not I concentrate from all the possible orthonormal bases to the standard basis, but still there are very many. So the problem still exists. Of course, I reduce a bit the size of the research, but it's still a big problem. Okay, this is the main theorem. Principal angle, okay. Standard basis, very difficult. And I say it here. I state the same thing here. The determination of the principal angles between a pair of subspaces is a well-known problem solved by the singular value decomposition of the orthogonal projector of S onto 2. So for the singular problem, for the principal angles would be no problem. So the problem to determine the SPN orbits of the k-dimensional subspaces turns into the one of determining the existence of the triple of bases belonging to B, the standard basis of S and the standard basis of T, which satisfy the condition 2, that the Gram matrices are the same in one space and in the other. This is not an easy problem to solve because, as already said, for any A, the standard bases are never unique. We have infinite, more or less. No, more or less, we have infinite spaces. An iterative procedure to determine a canonical form of the matrices of a subspace U that we denoted canonical matrices is given in my job, in the job that I said to you, where we have this theorem, we have also a procedure. The idea is to determine the triple of bases, satisfying the condition that we want to be satisfied, by using the uniquely determined standard subspaces UI, UJ, UK. These are unique, these subspaces, but the basis not of this form, respectively, and determining the mutual principal angles and associated principal vectors. So we consider these unique spaces, and we try to find among them the principal angles. Okay, and this will lead us to the determination of some unique vector. And from that, we can start to determine the basis. And I say this, but this is possible if at each iteration of the procedure, we have at least one principal angle with multiplicity 1. If all principal angles will have multiplicity 2, 3, 4, 5, then we cannot detect a principal vector, a unique principal vector. And this is a problem. And we cannot apply this procedure. In most of the cases, this procedure leads to the construction of the canonical matrices, and consequently to the full set of invariants, because what we need is these two matrices. But there are some degenerate cases where the aforementioned procedure cannot be applied to Kur. Okay, these are the degenerate cases that I don't know how to solve. Among these, there are the isoclinic subspaces. That is, subspaces characterized by the fact that for A in the sphere of complex structure, all principal angles between U and AU are the same, theta A, which is called the angle of isoclinicy. They do not exhaust all the degenerate cases, but surely they have an important role, and this article deals with them. Okay. Okay, I will, in the end of the article, let's go here. At the end of the article, I will find a solution to this problem. This is the good thing. I will define a pair of sets, name a triple of angles, A, alpha, beta, and gamma, and their cosines. Cosine alpha equals C, cosine beta equals K, cosine gamma equals eta. And a pair also, these are also scalar product cosines of some angles, gamma and delta. And I will prove that they are all invariants of U, and they determine the orbit. So I will show now what these things are. But anyway, these three angles and this also cosine of something, some angles, are invariants of U that determine the orbit. So if two subspaces have the same triple, the same pair, and of course also the three angles theta I, theta j, theta k, the principal angles, which is the easy part, then they are in the same orbit. This is the theorem I will show you later. This is the final result. Now, before going to the final result, I want to show something. Okay. This isoclinic subspace in dimension 2, all two planes, all subspaces of dimension 2 are isoclinic with I, U, J, U, and K, U. And it's easy to see that this implies that the U is isoclinic with respect to any A. If they are isoclinic with IU, JU, and KU, where IJK, I repeat, is hypercomplex spaces, then they are isoclinic with any A, any other compatible complex structure. Then the set of the Grassmannian of two planes and the set EC2 is the same thing. Instead, in dimension 4, this is not true. I mean, a subspace is isoclinic. Not all subspaces of dimension 4 are isoclinic. But if a dimension 4 subspace is isoclinic with respect to non-miscible basis, IJK, then it is isoclinic with respect to any A. But we need first to find that they are isoclinic with respect to IJK. In dimension 6, we have that, again, if U is isoclinic with respect to the miscible basis, then is isoclinic with respect to all. So 2 and 4 is the same. I mean, 4-dimensional, 6-dimensional are the same, have the same property. In 8-dimensional subspaces, instead, if they are isoclinic with IJK, then not necessarily they are isoclinic with respect to any A belonging to SQ. So when we deal with isoclinic 8-dimensional subspace, we have to put as hypothesis that they belong to isoclinic subspaces. It's not enough to say that they're isoclinic with IJK. In the other cases, it's enough to say that they're isoclinic with IJK. Let's just read the final part. Sorry, the final part. When I will say that something fixed, let's read here. Fixed on miscible basis H, IJK, we will say that some function from Cartesian product of V n times in R, we define some function. If these functions are constant on its domain, it means that it doesn't matter on the vector we take, we always give the same result, we'll say that A, the function A, is an invariant. Okay, but we have fixed ijk. If instead, not only is invariant, but it's also independent from the hypercomplex spaces, we say that this A, this function, is an intrinsic property of U. So to be intrinsic property is something more. It's an invariant with respect to any vector. Whatever vector I take gives the same result, but it's also intrinsic property. Whatever hypercomplex spaces I take, it's the same result. So invariant is less than intrinsic property. Allora, now here we said that we talk about 2-dimensional and 4 and 8-dimensional subspaces. The 2-dimensional already studied in slide 17. Here, you see there is my first article here. Orbits in the real Grassmannian of 2 planes under the action, 2 planes. So 2 planes are studied here under the action of the group SPN and also another group. So in this article, I developed a theory which reached the result for all 2-dimensional planes. Here, not only I consider the group SPN, but also the group SPN.SP1, which is the normalizer in SO4N of the quaternionic structure. SPN is the centralizer in SO4N in the special orthogonal group of the quaternionic structure. SPN.SP1 is the normalizer in the same in SO4N of the quaternionic structure. So it's a bigger, this is a bigger group than this. Okay, let's go to 17 again. Okay, here. Allora, for the 2 planes, in that article, I showed that we have this invariant. Oh, this is an intrinsic property. It doesn't depend on even on ijk. You take 2 vectors in 2 planes, oriented 2 vectors, okay. You make the Hermitian product. You divide it by the measure, and you get a quaternion, imaginary quaternion, which is always the same. Okay, any 2 vector you get, it's always the same result. Even if you change ijk, since I'll show you here. 17. At the beginning, no. You remember that the last line here, the Hermitian product you develop in this way. You take X and Y, then you have the hypercomplex structure I, J, and K, and you make this product. You may say that this number, of course, depends on I, this number depends on J, it depends on K. But if you, together with ijk, you change the basis I small to, let's say, from ijk, you get I prime, J prime, K prime. But together with ijk, in the isomorphism with I, small j, and small k, you get I prime, J prime, and K prime. So different coefficient, different element of the base, you get the same quaternion. So this imaginary, it's always the same quaternion, imaginary quaternion. Let's see again here. Okay, this imaginary is is an intrinsic property of the 2 plane. In every 2 plane, you get this quaternion, imaginary. Then it is shown in that article that here, the imaginary measure, this imaginary quaternion, represents the full set, the full system of invariants for the SPN orbits in the real Grassmannians of 2 planes, which is called 2,4n, and also 2 planes oriented to planes, because this is also a bit more articulated, this article. Okay, that is a pair of 2 planes here are in the same SPN orbit if they have the same imaginary measure. So to know if 2 planes are in the same orbit, you just take the imaginary measure 1, which is an intrinsic property, it's a quaternion, and another quaternion here. And if they are the same, they are in the same orbit under SPN. You can go from one to the other with the action of SPN. And this is in accordance with the general theorem which I developed in the successive article. Okay, this just showed this fact that in the successive article, I said that to be in the same orbit, you have to be to set the same principal angles and the matrix, invariant matrix Cij and Cik. And in fact, in all these two planes, the canonical matrices, I call them, are this, and the principal angles should be the same, of course, and then they are in the same orbit, also according to the general theory, let's say. For four-dimensional isoclinic subspaces, okay, it's a bit more complicated, but still it's understandable, let's say. The 8-dimensional case has a big and technique instead proof, which of course I will not show completely. I will just give a sketch because it's quite complicated, the 8-dimensional cases. The 4-dimensional cases, not so much. I would say that I consider now a 4-dimensional subspace. And suppose that the pair U and AU, A is one fixed, sorry. I would like to take away this. No. A and AU are isoclinic. Suppose that they are isoclinic. Then the A Kähler form with respect any orthonormal basis, x1, x2, x3, x4, has this form. 0, A, B, C, then these are the same, but with opposite. It's a skew symmetric matrices. Of course, omega A is a skew symmetric. So you have just to write these 6 numbers. And there are not even 6, are 3, apart from the sign that you have to know. Okay, this is the form of any 4-dimensional space isoclinic with A itself. U isoclinic with AU as this form. And of course, A square plus B square plus C square is the cosine. This is the matrix of the projector. Is the square cosine. Okay, there are the square root. Okay, anyway, the square plus the square is the square cosine of the angle of isoclinicity. Okay, so, and in fact, every line has the same. A square plus B square is the same number because every x3, suppose the third line, x3 is projected onto some vector whose norm is B square plus C square plus C square, which is exactly the cosine of theta A. Each vector, when you project, reduces the size to the same amount. Okay, now now we have seen a 4-dimensional subspace and its A image, and we suppose they are isoclinic. We say that we consider a subspace that is not only isoclinic with IU, but also is isoclinic with a triple IU, JU, and KU. And here I state that the proposition of 4-dimensional subspace isoclinic, we suppose that it's isoclinic and theta I, theta J, theta K, the angles, the 3 angles of isoclinicity, then it is isoclinic with respect to any A belonging to the sphere of complex structures. So it belongs, is U, once you see that it's isoclinic with HK, belongs to EC4, that is isoclinic with any A. From this to this is straightforward. I mean, this implies this, and of course, this implies this. The angle, if you want to know what's the angle of isoclinicity, theta A, between A and IUA is given by the trace, the square is given by the trace of omega A, which is the one of before, square. Okay, you take omega A, you multiply it by itself, and you calculate the trace, and then you divide by 1/4, and then it's the square cosine of the angle. So once you know the angles with IJK, you know all the angles. There is also this other expression. We don't need. Well, now what do we have? That we have this 4-dimensional subspace, which belongs to IC4. Now we said that it's isoclinic with everybody. Then we take a vector, any vector in U. When we project, it will reduce its size by cosine theta I, cosine theta J, cosine theta K. But any vector is a principal vector with IU, JU, and KU. Every vector reduces its size. So but of course, it will project on some vector, different vector, because they belong to different subspaces. And so if you take x1, then if you want to know what's a standard plane in U, you have to project x1 onto IU, come back with I minus 1, and you are back in U. You divide it by cosine I, and you obtain the second vector of the standard plane, the one which makes the standard form of omega I, the form omega is standard. You know, omega I as a standard form. If you take x1, then the second vector of the base, which determines the standard plane, is obtained in this way. You take x1, you project onto IU, and you get a vector in IU, which has the norm of this vector is cosine theta I times cosine theta I, because the first one is 1, its norm, it's long 1. Then you project, this projection is a vector in IU, which is long cosine theta I, which is its norm is cosine theta I. Then you come back with I minus 1, which is, let's say, in isometry, and we obtain the vector x2. The same here. You take x1, you project, you come back with j, and you obtain epsilon2, y2, dividing by a different cosine, of course. And also for zeta2, you get this expression. So these three vectors, x2, epsilon2, and zeta2, are the unitary vectors such that these pairs of three pairs are orthonormal standard bases of the standard two planes UI, UJ, UK. Now it's important. Now we prove something important. You take these three vectors, you make the scalar product. This cosine that you get, these are unitary vector. This is a cosine of an angle that we call xi, lambda, xi, chi, and eta are invariants of U. The same, wherever we take a different x1, then we get a different x2, a different epsilon2, a different zeta2. The scalar product of these three pairs are all the same. Okay, these three cosines. So are invariants of U. They do not. They depend, of course, on ijk, but at least they don't depend on the first vector. This we're not interested. Okay, we said that in this case, the procedure that in the four-dimensional case, we can apply the procedure that I put up in the other article, but we have just to add, to make it work, to overtake this problem, to apply that procedure, which means we just need to add one extra condition to the such procedure. Namely, when we choose the fourth vector of the basis, we have to we have to go to a specific vector, which we can have many possibilities for this triple, but we choose exactly one. Which is the one? Okay, it looks a bit technical, but I considered subspaces made, the two planes made of x2 and x4. Of x2 and epsilon2. Consider L. What is it? Here I don't see because it says something in front, but here it should be written, consider L x2 epsilon2. Then x4 and epsilon4 are of such two planes such that these, the x4 and epsilon4 are a pair of orthonormal bases consistently oriented, the orientation here is important, with x2 and epsilon2. So we detect x4 and epsilon4 by taking the vector normal to x2 in this subspace, which gives the same orientation of x2 epsilon2. Okay, so x2 epsilon2 L, x2 epsilon2 L means linear, I mean the span of these two vectors, two plane. This is a two plane. So we consider the two plane x2 epsilon2, and x2 epsilon2 gives an orientation. Then we want the other x2 and x4 keeps the same orientation, and the same epsilon4 gives the same orientation. The same we can do for x tilde 4 and zeta 4 in this plane. We take again normal here. This is a different plane, so we call it x tilde 4 because it's another plane. So x2 is the same, zeta, but the plane x2 zeta 2 is different from x2 epsilon 2. So we need x4 and zeta 4, and then also for y4 tilde zeta 4 tilde, we have a specific vector. We consider this vector by with this trick, let's say, just looking at the subspace two-dimensional and finding out the orthonormal basis. In this way, we have built up this, okay, but it's not finished. Then once you have x4, for instance, x4, you get x3 just in the usual way. Okay, once you have y4, you get y3. So you have now the 4 vector. X1 is the one you choose arbitrary. X2 is forced by these constructions. What is it, X2? X2 is forced here. And the same y2 and z2. So you have x1, x2. Then we also have x4 and we get x3. So the basis of this orthonormal basis are done. Here are the bases. This is one base, this is another, this is another, this is another, this is another. These are 6 bases of the same subspace U4 that are, I call it chains, center on x1, because x1 is arbitrary. So we could take another x1, but we have the same way to detect the whole basis with leading vector x1. I have to hurry up. Okay. Anyway, I jump, I see that, okay, this will lead us more or less with this basis fixed. I will show that I get to some matrices. Where are they? Aspetta, some matrices. These two, Cij and Cik, are 2 matrices that are this. Actually, let's go here. This and this, independent from the initial choice. So it's an invariant. They're invariant of U. So whatever U I choose, C, K, and eta are the same, but also this alpha, beta, and gamma, which are, I didn't say what are alpha, beta, and gamma, sorry. Okay, this is an important proposition that we needed. I say, let U in EC4, forget about 0, 1 orthogonal. The application mapping, these 6 chains, you change place, leading point, leading vector, to another leading vector, belong to the real representation of SPN. And SPN is transitive on all these 6 things. So you can go change point, you get to one set of chains, 6 chains, to the other set of chains by SPN, which means SPN is a subgroup SO4N, which means that all the scalar products are preserved. Okay, so this means that for any pair of chains belonging to this sigma, the relative gram matrix is an invariant. In particular, alpha, beta, gamma, which are the, I define it somewhere. Okay, let alpha, beta, gamma, the oriented angles, you see, in x2, y2, before we define the cosine, now we speak about the all angles. And here is beta, and here is gamma. So in this case, we have that these angles, not only the cosine, but also the angles are invariant, which is important because when you because later we need these numbers to write down these matrices, the canonical matrices, and these numbers are invariant, which means that if I change another x1, this matrix, which has the form gamma, gamma minus delta, delta, is an invariant, remains the same. So from this, we go to these 2 matrices, which depend, as you see, on beta, gamma, and delta, but beta, gamma, and delta are invariants. Alpha is an invariant. So these matrices are associated to the subspace. Doesn't matter which is x1, are always the same. And these are what we call canonical matrices. And so all 4, what's the conclusion? That all 4-dimensional vector spaces that they have the same theta I, theta j, theta k, okay. And then they have this matrix, which depends on alpha, beta, and delta, and gamma, are the same, okay, should be in the same orbit, if they have the same invariance. I will prove the gamma is a function of alpha, beta, and gamma, this big gamma is a function of alpha, beta, and small gamma. And then in the end, you see gamma is a function of alpha, beta, and gamma small. So what we really need to determine the orbit is exactly alpha, beta, gamma, and delta, big delta, because gamma is a function of these three. Okay. So proposition fixed on admissible basis, IJK to any U, we can associate. Actually, I should have finished at 50, not at 12. Okay. So we say theorem, the invariants alpha, beta, gamma, and delta, together with the angles theta I, theta j, theta k, determine the orbit of a U in a C4. Okay. So we have just to find out these four angles. I think that I don't have much time, so I better just make this okay. When we go to isoclinic space of any dimension, 2m greater than 4, we have the same solution. We prove that, similar to the result achieved in dimension 4, any U in IC2M, we can associate two sets of invariants, a triple and a pair, which determine the canonical form of these matrices, which is what we need, what we actually need. Since gamma is a function of alpha, beta, gamma, again, like I showed you before, according to this theorem, appear in my X publication, the vector alpha, beta, gamma, delta, and the triple of the three angles of isoclinicity determine the SP orbit of U. Okay, we prove the same thing. How to prove it's a bit technical, so I introduced this. Now I don't want to overload the audience, but I introduced this associated subspaces of type IUJ, UIJ, and UIK. It's a bit complicated here. I need more time to express this, but in the end, I will show that. Let's go straight to the end. Let me just say again, what are these four spaces that I need just to state the final proposition. I need just a little. Okay. I need just a definition, and I can try to state the result without proof and nothing. So we have a subspaces isoclinic of dimension 2m. We take x1 in each of them, and we generate, again, exactly the 6 chains we have seen in the 4-dimensional space. In this case, we obtain different subspaces. In there, we obtain different bases of the same subspace. Now, instead, we are in a bigger subspace, and with these 6 chains, we determine 6 different 4-dimensional subspaces. 6, because there are 6 chains, 6 bases, and they determine 6 different 4-dimensional subspaces in a bigger subspace. Okay, so I read it. We call associated subspace of type UJ and IAK a pair of 4-dimensional subspaces of type UJ and K generated by the omega I and omega J chains centered on a common vector. Okay, the final result is this one. Allora, we showed more or less that we can find a solution for all cases in all dimensions. So we have seen that in 2 dimensions we have solution, in 4 dimensions we have solution. Now we take U with a bigger dimension, 2m. We fix the basis, admissible, and we denote by theta I, theta j, theta k the angles isoclinicity of the pair U, U, IU, U, JU, U, KU. Then for any k greater than 0, if the dimension of this subspace equal 8k plus 2 or 8k plus 6, which is when you make division by 8, you get as rest 2 or 6, U is orthogonal sum of 2 planes isoclinic. So if we have a 10-dimensional subspace, this you can split in 5 times 2 planes, 2 planes. Each of them is isoclinic with I, J, K with the same angles. in this case, it's the simplest case. The orbit is determined only by theta I, theta j, theta k, and xi and k. So it reduces we don't have the whole subspace. In general, is this. Here we have this. So, okay, in dimension 10 or a k plus 2 or a k plus 6, for instance, in dimension 6, a 6-dimensional isoclinic subspace splits into the 3-dimensional orthogonal 2-dimensional subspaces isoclinic. And the orbit is determined by xi and k of these 2-dimensional subspaces, which is the same for all of them. If instead it's a multiple of 4, then U is orthogonal sum of 4-dimensional subspaces. And the orbit is determined by, no, here there is a mistake, should be small gamma here, alpha, beta, small gamma, and delta, okay? Because big gamma is exactly given by alpha, beta, and small gamma. If instead 2m is a multiple of 8, then, which is the most important result, the canonical matrices are determined by the whole set xi, k, eta, and delta. There is a mistake, alpha, beta, gamma, and delta. Alpha, beta, small gamma, and delta. Again, I made a mistake with small and big. And if in particular, then gamma square plus delta square equal 1, then we are in the previous case, the composition into 4-dimensional spaces. If in particular, xi equal plus minus 1 and k equal plus minus 1, then we are in the first case, the composition into two planes, isoclinic with the same angles of isoclinicity, that is theta I, theta j, theta k. Okay, this is the result. I had to make it shorter just to give an idea. Finished. Thank you very much.
Thank you very much for your presentation. I have a question to all. Do you have any questions?
Maybe I have just a very general question. Any possible applications in natural science and in technology in regards to your results?
I don't know.
I am physicist. I'm electrical engineer as well. I would like to know what type of how I can use your results for something useful.
I don't know. Somebody told me, somebody, a Russian professor, my advisor, told me that maybe some American guys were studying these things, more or less the same things, orbits in under some groups, action of some groups. For medicine, when you make TAC, how you say TAC? This, you know, when you make this X-ray, I don't know, TAC, how you call it in English?
Yeah. All right. Okay.
Okay, TAC. Then it can have some applications in this technique to find the best, the optimum planes, how to make these photos, let's say. This is the only thing I know about this. Then I just went into the mathematical point and I've forgotten the possible use. It's a typical mistake of some mathematics like me. But this is the only thing I know that can have some application in medicine for resonance for TAC.
There is also some recent work of Dr. Radosław Kycia in such direction. But anyway, thank you for your answer.
Professor who?
Professor Radosław Kycia has some results in this direction, I believe.
Okay.
He is on the audience, right?
Okay. Yes, thank you very much.
But that's why I raised it, because we already used Clifford algebras because Clifford algebras has very nice applications when you consider projections to the plane. So you can use it in this radiotherapy equipment, but these applications are also in spinors. Clifford algebras, ideal left or right ideal of Clifford algebra are exactly spinors. Well, algebraic spinors, so that's the whole physics can be applied using this Clifford algebras, which Massimo presented here. So it's very vast subject, I would say. Okay, thank you.
Thank you.
Thank you.
To you. Thank you very much.
Exciting presentation. I think that we can use it also in case of the analysis of the data using artificial intelligence systems, and also in case of the analysis of the particles near to the black hole, for example. It can be excellent approach. So thank you very much.
Thank you to you.
The next I have two announcements. The first, the presentation of